Our next presenter is Mike Hansen, who will tell us more about the suppression of lake trout on Lake Pend Oreille and the simulation efforts he's worked on.
Thanks, Mike. Thanks for coming. So Andy set the next stage here. This phase of the work now is where do we go next? The Idaho guys called me back into service and really posed two principal questions. How much longer will it take to reach the 90% level? And then when we get there, how do we keep them there? So I basically...
There we go.
Oh. Cool. Okay, so that's where I'll pick this up. Basically, I'm going to maybe skip this background. The previous two speakers were pretty good on that. I'll try to set up enough information on the model that you understand what we're doing with it and then focus on the results. The assumption I made in the original modeling exercise presented in Scotland was that the gill net fishing effort that was deployed would be configured in a certain sensible way. And this was turned over to professionals, and they do it, I don't know how, but it wasn't what I would have termed sensible. So that was one of the questions. Anyway, the background, the way I think of this problem is that the lake trout predominates in a whole lot of lakes in North America. I reviewed that earlier in the symposium, but it was introduced widely, and the lake trout tends to overwhelm those systems. And Andy and Dan covered some of that. So the question here is about suppression, and then lastly, how can we design this suppression program? I think there's an element of this that I completely forgot about the first time through, and I'll come back to that. So there's several questions. Which combination of gill net mesh sizes would minimize time to reach target abundance? This was the thing I completely missed the first time around. In other words, you have to tell these professionals which meshes to use and how much. That really has a huge effect, as you'll see in a minute. And then once you figure that out, the second question here was, what about this trap net thing? How efficient is that? And is there a way of judging the equivalency of it to gill netting? We then said, okay, now how much longer? And we figured out how to fish the nets and how much. How much longer will it take if we use that optimal selection method? And then finally, once you get there, how much can we ease back on the gas pedal? Because this is a pretty expensive program, and you would like to get a maintenance of a low level of fish, hopefully with less effort. Okay, so the model. Some of you are old enough to know what this is. This is in my house with my brother or something. All right, so the whole project is inside a computer where things are safe, cheap, and then the hard part comes when I tell these guys, well, here's what you should do. Easy for me. In this case, basically built a model and run lots of simulations, keeping track of how many fish are in the population. How many times does it collapse? And how long does it take to collapse? Very simple stuff. And here again, I'll just reiterate that the definition of collapse here is to reach that 90% suppression. So measured against where we started, the population peaked in 2006, but it came from an abundance in 1999 when no one even knew they were there. So that's where that 90% came from. So the model is a very simple age-structured model, and as is my want, I tend to make things more complicated through time. So the old model that was presented in Scotland got considerably more complicated this time around. But basically, it starts with you have to bring some babies into the population, and then you have to subject the ones in the year classes to mortality. So this is that graph Andy showed you. The first point here is we had to create a starting abundance, which is the abundances, the age-structured abundance on the right-hand side here in 2016. That's where we start the model and then run forward from there. Recruitment, this population hasn't been studied well enough to know about this part of it. So we basically used a very intensively studied population in western Lake Superior as the baseline recruitment model, where you can pick from this MC-MC distribution of the two parameters in the Ricker model. And then the recruitment process error, epsilon here, is a random variable. So for each iteration, each year of each iteration, there's a different set of parameters. This accounts for what the modeling geeks call a parameter uncertainty. In other words, you have to account for this directly inside the model, or you're making some huge assumptions about how much you know. In this case, we borrowed this stuff from Lake Superior under the assumption that Ram Myers was the genius he was, that alpha, for example, is a fairly invariant parameter associated with a certain fish. And then we decided to scale the abundance predicted by the model to Flathead Lake, the density there, because that's another western lake real nearby, rather than assuming the density would rise to what it might be in the native range, where there's a more connected ecosystem that might look different. The density in Flathead Lake is higher, if you saw my talk earlier in the week, than in the native range. So this is a conservative assumption. Assume it might be a higher carrying capacity. Natural mortality I modeled with the relatively well-cited Pauli equation, only in this case I treated it again as a random variable. I drove the model with the parameters of Pauli's equation, but they were treated as random terms, and it gives you a distribution of M something like this. So every year of every iteration has a different value for M. That's parameter number 2, acknowledging uncertainty in what we know about it, and having that fly right through the simulations. Mortality sources, there were 3 of them, as you saw from Andy's talk. Treated these as an implementation error. We now, with 10 years of data under our belts, we know that you can specify how much you want to fish, but there's a question about how much will happen. This is the angling relationship from some of the stuff you saw earlier, and you can see there's a pretty strong density dependence in angling. The point here is that no matter how much you pay anglers, when fishing gets lousy enough, they lose interest. So you can't depend on them. So in this case, angling is treated as simply a density-dependent mortality function with wide uncertainty. That uncertainty then reflects the implementation error that one would expect. It has a strange relative selectivity, but well understood now with lots and lots of information. So basically, angling is set as a random, fully selected fishing mortality for each year of each model iteration. On to trap nets. This is the one that we eventually dropped from being in use, but here's how it looks. The trap netting fully selected fishing mortality rate varies along a linear pattern with the number of net nights that you're purchasing out of the commercial guys. But the implementation error is if you set how many net nights you want, you get a wide-ranging result possible. It has a fairly describable selectivity that tends to favor fish near when they fully mature. And so inside the model, this is again a random variable set each year of each iteration based on that selectivity and the level of net nights you buy essentially in the contract for the commercial fishermen. Gill Nets, a little more complicated, and this was the part that I got so wrong early. Basically, when you decide how many millions of feet you want to buy, there's a wide possibility over what you'll get in terms of fully selected F, and then you're also purchasing mesh sizes. These guys are creative folks. They probe with different mesh sizes, but we wanted to decide what is the optimal configuration of mesh sizes for the purpose of rapidly punishing the population. Remember, they're not a bad fish. They're just misbehaving and they need to be punished. So this again is a random variable inside the model, invoking again that implementation error. But you have to basically decide how much of each mesh to fish. That becomes one of the study objectives. Okay, so that's how the model is running. There's a lot of parameter uncertainty. There's a lot of implementation error. It's all accounted for. Not every possible source of uncertainty is, but those are the ones that are. So the first question we asked, which combination of gill net mesh sizes would minimize the time to reach target abundance? You can get this totally wrong. If you fish the wrong mesh sizes, it takes you twice as long. So this was a vexing problem for me to solve. Basically, you can run the model for any individual mesh size, and you quickly learn that not all meshes are created equal. This is a graph with mesh size on the x-axis, years to reach target abundance on the y. And you can see that if you fished 38 millimeter stretch measure, it'll take you forever. If you fish large meshes, it takes you less time. Message number one, if you want to punish lake trout, kill the adults. Focus on the adults. There's also very effective meshes in the middle, the 51 and 64. It's showing you that if you do kill the subadults, that can be effective too. And that again gets to what Andy talked about, the pinch of killing adults and juveniles simultaneously. Well, this is the optimal mesh size to absolutely minimize the time to reach the target. And notice there's a high reliance on the very largest mesh and then a couple in the middle. So this was the revelation of this whole project. Now we know what we should fish to reach the target. Remember, this isn't a commercial fishery. People don't connect the dots here. In the commercial days on Lake Superior, 114 millimeter mesh was the most popular mesh simply because it delivered the perfect fillet to the restaurant market. And they weren't trying to crush the population, they were just trying to make a living. Our objective is different. This is the mesh configuration that would optimize achievement of the objective. Okay, now taking that optimal mesh size, let's examine how much longer. So how much gill net, in this case, we're asking this question, what about trap nets? What's the equivalency? This is the equivalency with mesh size now on the x-axis, with a percentage that you could configure with gill nets to exactly mimic trap net fishing. Unfortunately, for trap nets, you fish them for a long time to make the equivalent of a very little bit of gill net effort. The punchline here for me was trap netting 14 weeks can be replaced by 1 to 2 weeks of gill netting. And if you use the optimal mesh size, it's only 1 week. So think about that in terms of cost benefits if you're the guys writing the contracts. Now let's get to the big questions. How much fishing effort is needed to suppress lake trout abundance? 90%. Here's the years to reach target abundance as a function of gill net effort, in this case meters, millions of meters on the x-axis. On the far right side, we're anchoring the maximum amount of gill net that can be afforded. And the good news here is that you can see at that level of peak gill net use, you could reach target abundance in about a decade. So that's the good news. Another 10 years and we can reach the target. Unfortunately, none of the mesh configurations that were fished in the period that Andy just covered are nearly as efficient as if they had used the optimal mesh configuration. So all of those uses were much less efficient. In fact, the effort allocations were so much worse, they were basically costing us time to reach suppression. That's the part that I got wrong in the previous modeling exercise. All right, so now we know we can reach target in a decade. What next? What would we do to sustain that reduced abundance? The cool thing is, I've got the target abundance here as the horizontal dash line. You can dial back quite a bit. With the same x-axis here, you can dial back a lot. In fact, you can cut back something like 85%. So that's the good news. Once you reach target, dial it back and keep the population in a stranglehold. And again, none of the previous configurations of meshes were nearly as effective. They cost you roughly twice, you leave twice as many fish in the water, 1.7 times to 2.6 times. All right, let's wrap up. That is a kokanee. Not only that, it's a big kokanee. It happened to be one of those I saw. I only saw 3 of them when I was there. They were so scarce. So, punchline, optimizing effort among gill net mesh sizes would minimize the time it takes to reach the target. And you can basically swap out a week of gill netting to accomplish what you were doing with 14 weeks of trap netting. Continued gill netting at that current effort would suppress abundance by 90%, and these are the limits of confidence that embrace all of those sources of uncertainty, possibly as few as 7, but maximally around 13. And then when you get there, you could dial it back by 76 to 86%, and here the range is, you got to choose. Would you guess on the low side? I think if you're conservative, you'd say, no, let's guess on the high side, just to make sure we maintain the population in a suppressed state. And now I'm going to doff my hat to this guy. He referred to himself as the dwarf. This is Ned Horner, and I've lived my life realizing that key people in key places at key moments make things happen. Ned Horner was a guy in the back of the room when I was in a Flathead review. Everyone's wringing their hands. How are we going to get rid of these lake trout? I said, why don't you just kill them? We can't help but kill them in their native range. Why don't we just try? Ned heard that several weeks later. He called me. He says, hey, can you help us out here in Flathead Lake? And that led to a sabbatical. It led to a model. It led to what Andy just showed you. But this program was like taking a poke in the eye with a sharp stick. And it takes a guy like Ned, the dwarf, to do it. People with less courage would not have bothered because it was too hard. There were a lot of people that loved lake trout, and this was not pleasant. I was there for a year working with that Lake Pend Oreille management committee, bringing them a model back every month and working through this public involvement program. It was a lot of it goes to Ned, and then also to Ned's boss, who happens to be young Corsi's dad, the regional director, to back up Ned. This would not have happened without those two people, and this guy's largely responsible. He's the guy on the ground, locally, getting poked in the eye every week. It was amazing to watch. And, thanks. Kurt?
That was amazing. To add even more complexity, is the avoidance of mortality for bull trout simply a spatial thing, or could that factor into your gill net selection to give you even more modeling to do that you obviously love to do? So.
That's a great point. It's easy for me to say, well, you should fish these meshes and build up the amount of large meshes, but the rub is how do you do that without killing too many bull trout? It's exactly the problem, and I'm glad it's not mine to deal with. Matt and Andy have to deal with that. If you really want to kill lake trout, how do you do it without killing too many bull trout? The earlier version of this model had bull trout in it simultaneously, and avoiding them is a problem. But these guys that are doing this netting are masters at this. They probe. Bull trout bycatch too high, you go away. They have figured out not how to make it zero, but how to minimize it. And maybe you guys can tell them how many are being killed. I don't know what the take limit is, but it's a problem.
I guess the good news is you ramp up and then you scale back to this maintenance, and that would help, right?
Mike, what do you think accounts for the gap in your mesh? I mean, you have medium mesh and then large mesh. Is it a placement, or is it an interaction with bull trout? Why would those just about large meshes not be effective?
Mark, I'm not sure I know. Are you asking why the difference?
Well, I'm fascinated that there's a gap in the mesh series for the most effective combination of meshes.
Yeah, and that's a great question. I got stuck on this problem for a long time, and I'm not exactly sure. I have a feeling that it's always better to fish on both the adults and subadults, but it's clear to me that the punch in the eye that works most is the adults. And we know from experience in these Great Lakes that large mesh gill net fishing was a huge force that drove the populations down. The thing I've always believed from a paper that Eschmeyer wrote, when he finally monitored the deep chub net fishing, small mesh fishing in Lake Michigan at the point where the stock was collapsing, there was a lot of baby lake trout being killed. It was not monitored, it was not quantified, and that fishery was very robust. And it was out there where the babies were. So it's just one of those unquantified pieces of the puzzle that I happen to believe a lot in, and maybe I'm just believing it because I want to. But notice the combination. Some of those mid-sized meshes, along with those big ones, seem like it's the crucial mix. And I can't explain exactly why. I think your question is excellent, though. Is that it?
Thank you, Mike.